So in this class I will teach you again about rectifier. In previous class I taught you about half-wave rectifier circuit. Okay, so the main function of any rectifier circuit is that it converts AC into DC. Suppose input is 220 volt and say 50 hertz. This is the power supply. Okay, now it can be converted by using transformer. It can be converted to again AC signal but having lower Vm. Okay, then it is given to rectifier circuit. So the output of rectifier circuit, it is pulsating DC. What is this pulsating DC? In pulsating DC signal, here AC and DC components are present in the output of any rectifier circuit. So we have to use another circuit that is known as filter. So the main function of filter circuit is to eliminate the AC component in the output of the rectifier circuit. Okay, so when the output of this rectifier circuit is connected to filter circuit, then the AC component, it will be removed and only DC component will pass. So finally after the filter circuit, it will be complete DC signal. Okay, complete DC. Okay, so the function of rectifier circuit is to convert AC to DC, and if we are using filter circuit, then it is completely converted into DC signal. Okay, so in previous class I was teaching you about half-wave rectifier. Okay, so what you have seen in half-wave rectifier circuit? Say this is RL, this is diode D, and this is transformer. This is AC input. Okay, now it is Vm. What is Vm? Vm is the peak value of the AC signal that appears across the secondary of the transformer. This is primary side and this is secondary side of the transformer, and it has say N1 and N2. These are the turns ratios of a transformer. Okay, so in case of half-wave rectifier circuit, we may use transformer or we may not use transformer. But why we are using this transformer? First is we are using the transformer either to step up or step down the input voltage, this input voltage, AC input voltage, and second, to prevent electrical shock. This transformer provides isolation between this AC input and this rectifier circuit. Okay, rectifier circuit consists of this diode and this RL. Okay, C, and this is V out. So this is the diagram of a half-wave rectifier circuit by using transformer. We may not use transformer also. So in that case, the circuit will look like this. say V in. Okay, so V in, it is equal to say Vm sin theta. And how you are representing V in? Here it is Vm and it is minus Vm. Theta is this theta, 0, pi, 2 pi, 3 pi, 4 pi. Theta is what? Theta is omega t. Okay? And time period is, this is the time period t. It is clear? So this is V in and this is peak amplitude of V in. This is Vm plus Vm and this is minus Vm. Okay? V in is equal to Vm sin theta, where theta is equal to omega t. Okay? Now in the output, the waveform will be like this. You have seen in previous class all these. Okay? Now in a half wave rectifier circuit, I RMS or IAC, it is equal to how much? It is equal to Im by 2. Similarly, Vrms, it is equal to Vac, it is equal to Vm by 2. Vm is the peak amplitude of the input signal, okay, that appears across the secondary of the transformer. Okay, now you have seen in last class this, and similarly IDC, it is equal to Im by pi, and VDC, it is equal to Vm by pi. Okay, like this. Then in a half wave rectifier circuit, you have calculated that we have calculated efficiency, it is equal to P out divided by P in. Okay, so it is equal to P out, it is equal to IDC square into RL, this RL, divided by P in, it is IRMS square into RF plus RL. Okay, P out, this is output across the load, and input, P input signal, power in, power out divided by power in. So it is equal to how much? IDC, it is equal to Im by pi whole square into RL divided by, it is Im by 2 whole square into Rf plus RL. So in previous class we have seen that efficiency in terms of percentage, it is equal to maximum efficiency. First we have seen efficiency, it is equal to 0.406. Okay, in terms of percentage it was 40.6%. Okay, this is maximum efficiency in case of half wave rectifier circuit. Then we have seen F out, frequency of output signal. Frequency of output signal will always be equal to frequency of the input signal in case of half wave rectifier. Okay, to This is second one. Then third one is the ripple factor. How to calculate the ripple factor in case of half wave rectifier? Okay, so ripple factor. What is ripple factor? Ripple factor, it is, see, in case of half wave rectifier circuit, the output is like this. Okay, so output contains, this is say omega t versus V out, and it is Vm. Output of a half wave rectifier circuit, it contains DC as well as AC component. Okay, so ripple factor, it is equal to the ratio of is RMS value of AC component divided by DC value of the output signal of a rectifier. It is known as ripple factor. So this is the output signal. In this output signal, AC component as well as DC component both are present. So ripple factor, it will be calculated like this: RMS value of this AC component only divided by DC value of output. Okay, like this ripple factor. So how we can calculate the ripple factor for a half wave rectifier? See, I RMS of AC component. Okay, in case of half wave rectifier, it is equal to I RMS of the complete load current which contains both AC as well as DC minus IDC square. We can write like this. So ripple factor, it is equal to I RMS only AC component divided by IDC. By using this formula, we can calculate the ripple factor. So I RMS AC component only, it is equal to I RMS of the load current. This load current that appears across this RL, okay, minus IDC square. Okay, so it is equal to, so we can find ripple factor like this: I RMS, then again this is say equation A. Okay, now if we are dividing this with IDC, so this is ripple factor, so it is equal to, then again we have to divide it with IDC. So we are getting I RMS AC divided by IDC, it is equal to what? It is equal to under root of, we have to, it is equal to I RMS divided by IDC square minus 1. So this is the formula for calculating ripple factor in case of any rectifier circuit. Okay. Now in case of half wave rectifier, I RMS, it is equal to how much? It is equal to Im by 2. and IDC. How we can calculate? How we can write? IDC it is equal to Im by pi. Now we can substitute these values in this equation. So ripple factor it is equal to under root of IRMS. It is Im by 2 divided by IDC. It is Im by pi whole square minus 1. Okay, so it is equal to pi by 2 whole square minus 1. So it is equal to 1.21. So this is the value of ripple factor in case of half wave rectifier circuit, that is 1.21. What does this signify? See, ripple factor, if ripple factor of a rectifier circuit is more, then we can say that this rectifier circuit is not efficient. It is not efficient. Okay. Now, for ideal case, ripple factor should be 0. Then in that case, complete. Then in that case, AC component in the output it will be 0. Then only ripple factor will be 0. Okay. So for a complete DC signal, ripple factor will always be equal to 0. Okay. Now in case of half wave rectifier circuit, ripple factor it is equal to 1.21. This is very high. So the half wave rectifier circuit is generally not used for practical rectification. Okay. Then we will study about peak inverse voltage. For a half wave rectifier circuit, the peak inverse voltage it is equal to Vm. What is this Vm? Vm is the, suppose Vin it is equal to Vm sin theta. We have just seen Vm is the peak amplitude. Vm is the peak amplitude of the input signal. Okay. What does this peak inverse voltage mean? What this signifies? This is the maximum voltage that can be tolerated by a PN junction diode in reverse bias condition. Okay. Suppose this is the circuit diagram of a half wave rectifier circuit. This is RL and this is diode D and this is Vin. So Vin is equal to Vm sin theta. Okay. Now in reverse bias means this is open and this is plus minus Vm. Suppose this is plus minus Vm. Okay. So this is peak inverse voltage. So peak inverse voltage is the maximum reverse voltage that a diode can tolerate in reverse bias condition. Okay. So in case of half wave rectifier circuit, it is equal to Vm. Now we will study about full wave rectifier circuit. So we will study about two types of full wave rectifier circuit. First one is center tap full wave rectifier circuit. and second one is bridge rectifier full wave. Okay, so first of all we will study about center tap full wave rectifier circuit. The circuit diagram will be like this. Here we can write CT. CT stands for center tap full wave rectifier circuit. Say this is RL and this is output V out. This is the circuit diagram of a center tap full wave rectifier circuit. Okay. See, this is VAC and this is transformer. Okay, and this is the center. This is the center of the secondary of the transformer. Okay, and this is load. This is diode D1 and this is diode D2. Then what is the working principle of this center tap full wave rectifier circuit? Okay, we will see. Suppose it is Vm and here it is Vm. See, during positive half cycle, if we are applying the signal, input signal, and we are using transformer, okay, so during positive half cycle, across the secondary terminal of the transformer, the polarity of the voltage will be like this: plus, minus. It is plus and it is minus. You can see here it is plus, here it is minus, here it is plus, and here it is minus. During positive half cycle, means from, suppose this is T, so 0, T by 2, T, like this. From 0 to T by 2, the input cycle, the positive input cycle, for this positive input cycle, the polarity across the secondary of the transformer will be like this: positive, negative, positive, negative. Here it is Vm and here it is Vn. Okay. Now this positive, this is positive, and this is P side. This is P side and this is N side of the PN junction diode. This is P side and this is N side. Okay. So this P and this is this positive and this P. Okay. So because of this, positive is connected to the P terminal. It is in forward bias condition. So in forward bias condition, we can replace this diode with short. If we are considering diode as idle, then in forward bias condition it can be replaced with a short. Now here it is. This is negative and negative potential is connected to P side of the diode. So it is in reverse bias. So diode D2 is in reverse bias. So we can represent this with open if we are considering diode as idle case. Okay. So for the input signal from 0 to T by 2, okay, for this time period, this diode is in forward bias condition, diode D1, and diode D2 is in reverse bias condition. So this is represented by a open switch. This is represented by a closed switch. So current will flow from this positive, means from higher potential to lower potential. So how current will flow? Like this. Okay. So V out it is plus and it is here it is minus. Okay. So output will be, you can plot the output wave also. So we have to erase this first. This is positive, negative, and this is positive. This is V in versus time t, 0 t by 2, this is t, then 0 t by 2, this is V out versus time t. Okay. Now during positive half cycle, during this positive half cycle, D1 is on. For this D1 is on and diode D2 it is in reverse bias condition. Okay, so output will be output that appears across this load. It will be the same. Suppose its magnitude is Vm, peak amplitude it is Vm. It will be like this. So voltage drop across this RL, it is V output. V output it is equal to like this, the same V in. Now during negative half cycle, we have to see during negative half cycle how it works. Again the same figure. So for negative half cycle means from t by 2 to t, okay, the polarity will now change across the secondary terminal of the transformer. Here it is Vm and here it is Vn. Now this is negative potential and negative potential is connected to P side. So this diode D1 is in reverse bias condition. So reverse bias condition means we can replace this diode with open, and this plus it is connected to P side of diode D2. So it is in forward bias condition. So in forward bias condition we can replace this diode with a short. So how current will flow? You can see current will flow like this from positive terminal, again like this way. This is the direction of the current flow in during negative half cycle. Okay. Then we are seeing that this is the same polarity, output voltage we can take it across RL. So the polarity is not changing for positive half cycle also, and for negative half cycle polarity of the output voltage it is not changing. So it will be like the same like the previous one. Okay. So in this case we can see D1 it is on, diode D2 it is off. Here diode D1 is off, diode D2 is on. Like similar way it will be like this, and maximum amplitude it is Vm. Okay. So this is the working of a center tapped full wave rectifier circuit. So for a center tapped full wave rectifier circuit we can calculate we can calculate the various parameters of a center tap full wave rectifier circuit. Here I RMS, it is equal to Im by root 2. Similarly, V RMS, it is equal to Vm by root 2. This is first case, and second case is VDC, it is equal to 2 Vm by pi. IDC, it is equal to 2 Im by pi. In case of half wave rectifier circuit, IDC it is equal to Im by pi. Here it is 2 times as that of a half wave rectifier circuit, because in case of half wave rectifier circuit we have seen that during 0 to t by 2 and from t, during only positive half cycle we were getting the output, and from t by 2 to t it was 0. Okay, so DC, see VDC it was Vm by pi. Now in case of full wave rectifier circuit, here we are getting like this. This is say Vm. Okay, now here it is from 0 to t by 2, from t by 2 to t the same signal, so it will be 2 times 2 into Vm by pi, 2 into Vm by pi. For IDC it is again 2 into Im by pi, where Vm and Im these are the peak values of the input signal. Similarly, IRMS and VRMS can be calculated like this, where this is the Vm is the peak value of the voltage of the input signal, and this is peak value of the current, input current. Now, how we can calculate the efficiency? Rectifier efficiency in center tap full wave rectifier. How we can calculate the rectifier efficiency in center tap full wave rectifier circuit? Okay, just like previous one, efficiency it is equal to P out divided by P in. So it is equal to P out, it is equal to IDC square into RL. P in it is equal to IRMS square into RF plus RL. What is RL? RL is the load. RL is the load, that is across this load we are measuring V output. Okay, and this RF, what is this RF? Small RF. RF is the resistance of the diode in forward bias condition. This is the resistance of diode in forward bias. Okay, generally RF is very much less as compared to RL. Okay. So it is equal to IDC. What IDC? In case of, this is in case of center tap full wave rectifier. Okay, so IDC it is equal to how much? IDC is 2 Im by pi whole square into RL divided by IRMS, it is Im by root 2 square into RF plus RL. Okay, so after final calculation it will be like this. is 2 times of 0.406 into 1 divided by 1 plus RF by RL. We can write like this. So it is equal to 0.812 divided by 1 plus RF by RL. Okay. Now in general case, RF is very small as compared to RL. So if RL is very much more as compared to RF, then we can neglect this RF. So efficiency maximum, it is equal to 0.812. So efficiency in terms of percentage, it is equal to 81.2%. It is maximum value. Okay. So in case of center tap full wave rectifier, what we have seen, in case of center tap full wave rectifier circuit, maximum efficiency, it is equal to 81.2%. Okay, rectification efficiency. And then we will see output frequency, F out. In case of full wave rectifier circuit, suppose the input is like this. Say this is V in and this is Vm and this is minus Vm. Vm, it is the peak value of this input signal. This is say 0, T by 2 and this is T. Output signal, it will be like this. Again, here it is. This is Vm and V out versus T. Okay. Now, in this figure, we are saying that this is one time period and here this is one time period. Okay. So time period of input signal, you can see time period is 2 times as compared to the time period of the output signal in case of full wave rectifier. So output frequency, it will be equal to 2 times that of the input frequency. Because time period, here it is T by 2 and here it is T. Time period is T and here it is T by 2. T by 2, T by 2, like this, T by 2. This is time period, complete time period. Okay, so this time period, you can write time period, it is equal to what? This is T, this T, this T. So this T by 2, again T by 2, T by 2. So frequency is inversely proportional to time period. So we can write F output of a full wave rectifier circuit, it is equal to 2 times the input frequency. So suppose the input signal, it has frequency of say 100 Hz. Okay, then the F output, its frequency will be 2 into 100 Hz. Okay, because this time period it is reduced to half as compared to the time period of the input signal. Okay, and time period and frequency both are inverse in nature, both are inversely proportional. So we can say that F output, it is equal to 2 times F in case of full wave rectifier circuit, but in case of half wave rectifier circuit, F output, it is equal to F in, because the time period of the input signal and output signal both is same in case of half wave rectifier. Okay, but here we are saying like this, here it is T and this is T. Then we will study about peak inverse voltage. How to calculate the peak inverse voltage in case of center tap full wave rectifier. So again, for this we have to draw the circuit diagram. See, peak inverse voltage can be calculated during reverse bias condition only. So during reverse bias condition, suppose for this negative half cycle, this diode, it is not conducting, and here it is minus plus Vm, minus plus Vm, and this is RL, and V output, it is again Vm, okay. So direction of the current, it is like this. So here it is again positive and here it is negative. So peak inverse voltage, it is equal to Vm plus Vm. This Vm is the voltage across this secondary of the transformer. This is center tap, this Vm, and voltage across RL. This Vm is voltage across the secondary of the transformer, and this Vm is the voltage across this RL. So in case of full wave center tap rectifier circuit, peak inverse voltage is we are seeing that it is 2 Vm. Okay, then we will see ripple factor. Ripple factor in center tap full wave rectifier. How we can calculate? Again by using the same formula. It is I RMS component of AC divided by I DC. So how we can calculate? It is equal to under root of I RMS of the load current divided by I DC square minus 1. In case of full wave rectifier circuit, I RMS, it is equal to how much? It is equal to Im by root 2. Similarly, IDC, it is equal to 2 Im by pi. If we will put these values in this equation, then what we will get? It is value IRMS is Im by root 2 divided by IDC is 2 Im by pi whole square minus 1. So it is 0.482. Okay. So the ripple factor in case of center tap full wave rectifier circuit is equal to 0.482. So in case of half wave rectifier circuit, ripple factor was 1.21. This is in case of half wave rectifier. In case of center tap full wave rectifier circuit, ripple factor is 0.482. So we can see that we are saying that here the AC component it is reduced. in the output. Here the AC component in the output is very high as compared to center tap full wave rectifier circuit. Here it is lesser the ripple factor, better will be the rectifier circuit. Okay, so this signifies that in case of center tap full wave rectifier circuit, in the output, this is the output of a center tap full wave rectifier circuit. In the output, see AC plus DC component, and in case of half wave rectifier circuit, like this. This is for half wave rectifier and this is for center tap full wave rectifier. Here we are saying that the DC component, by analyzing this ripple factor, in case of center tap full wave rectifier circuit, it is coming as 0.482, and in case of half wave it is 1.21 and it is 0.482. Okay, so here the AC component is lesser and here AC component it is more. That is why here the ripple factor is 1.21 and here the ripple factor is 0.482 only. Okay, so in this way we can calculate the various parameters in case of center tap full wave rectifier. The main difference between half wave rectifier and center tap full wave rectifier circuit is that here in case of center tap full wave rectifier circuit, we have to use center tap transformer, but in half wave rectifier circuit we may use a transformer or we may not use a transformer. Okay, but here we have to use only center tap transformer. Okay.